You're listening to Scientific Giants Who Change the World. Each episode stands beside one mind and follows a thread of curiosity until it ties to the world we inhabit. Today, we enter the quantum revolution. At the moment it stops being a collection of clever fixes and becomes a new mechanics, a new way of building physics from the ground up. The person at the center of this episode is Werner Heisenberg, a man whose name has become shorthand for a truth that feels almost like a philosophical provocation. At the smallest scales, the more precisely you know one thing, the less precisely you can know another. But if you want to understand Heisenberg, you have to see him not as a slogan, but as a human being, caught in a century's storm, scientific, political, and personal. You have to see the uncertainty principle not as a mystical statement about mystery, but as a hard constraint, woven into the mathematical structure of quantum mechanics, discovered by someone who was trying above all to be honest about what could be observed and calculated. Heisenberg was born in 1901 in Würzburg, Germany, into an educated family. His father was a professor of classical philology, which meant that Werner grew up in a world where language, rigor, and disciplined thinking were valued. He came of age as Germany convulsed through World War I and its aftermath. The world he inherited was unstable, wounded, hungry for order. For a young mind with talent, the desire for structure can become a kind of refuge. And physics, especially the kind that promises deep laws, can look like the purest form of order available. He studied physics in Munich under Arnold Sommerfeld, one of the most influential mentors of the era. Sommerfeld's students were trained not only in mathematics, but in a kind of pragmatic theoretical craft. How to use approximations, how to extract predictions, how to connect theory to spectra and experiments. The old quantum theory, the patchwork of quantized orbits and ad hoc rules built by Bohr and others, was still the dominant framework. It worked in some cases, but it was fragile, inconsistent, and increasingly unable to handle more complex atoms. Young physicists of the early 1920s lived inside that tension. They had glimpsed the quantum world, but did not yet have the full language to describe it. They were building a new physics with tools borrowed from an old one, and the seams showed everywhere. Heisenberg was part of this generation, and he was unusually sensitive to the foundational problem. Classical pictures were failing. The attempt to imagine electrons as little planets orbiting a nucleus with well-defined paths was producing contradictions. Yet the experimental data, spectral lines, intensities, selection rules were precise and demanded explanation. Heisenberg's breakthrough began with a kind of intellectual austerity. He decided to throw away what could not be observed. This sounds like a philosophical slogan, but for Heisenberg, it was a practical method. In the quantum domain, you do not observe electron orbits. You observe spectral frequencies and intensities, transitions between states. You observe energy differences. The orbit itself, as a classical trajectory, was not an observable. So why build your theory around it? Heisenberg's idea was radical in its simplicity. Construct a mechanics based only on observable quantities, quantities tied to transitions between measurable energy levels, rather than on unobservable classical paths. In 1925, while suffering from severe hay fever that made life in the city miserable, Heisenberg retreated to the island of Helgoland in the North Sea. The island setting has become part of the myth. The young physicist alone on a windswept rock, feverish, wrestling with equations late into the night. The myth exaggerates, as myths do, but it captures something true. Heisenberg was under intense pressure, internally and externally. He knew the old theory was failing. He knew something new was needed. He also knew he was close to a breakthrough, and closeness can be psychologically brutal. On Helgoland, he developed a new way of representing physical quantities. Instead of describing an electron's position as a function of time along an orbit, he represented quantities as arrays of numbers tied to transitions between states. These arrays were soon recognized as matrices. And crucially, the multiplication of these quantities was non-commutative. A times B was not necessarily equal to B times A. That mathematical feature, non-commutativity, turned out to be the signature of quantum mechanics. Heisenberg's paper, with the help of Max Born and Pascual Jordan, became the foundation of matrix mechanics, the first complete formulation of quantum mechanics. It reproduced known results and provided a systematic way to compute new ones. But perhaps more important, it shifted the conceptual ground. Quantum mechanics was not going to be a modified classical mechanics with a few quantization rules. It was going to be a different algebra of nature. It is easy to miss how shocking that was. Classical mechanics is built on commutative quantities. Positions and momenta are numbers you can multiply without worrying about order. The new mechanics suggested that in the quantum world, the order of operations matters. Measurement-like operations do not commute. The very structure of description has changed. Soon after, in 1926, Schrödinger introduced wave mechanics, an apparently different formulation that described particles as wave functions evolving smoothly in time. At first, there was competition and confusion. Was matrix mechanics real, or were waves real? But it became clear that the two formulations were mathematically equivalent. They were different languages describing the same underlying theory. This is already a hint of Bohr's complementarity. Multiple representations may be necessary, and no single classical picture will be sufficient. In 1927, Heisenberg articulated the uncertainty principle. This is the idea most people know, but it is often misunderstood. The uncertainty principle is not a statement about sloppy instruments or human ignorance. It is not merely that we disturb a system when we measure it. That disturbance story can be a helpful intuition, but it is not the essence. The essence is mathematical and structural. In quantum mechanics, certain pairs of observable quantities correspond to non-commuting operators. The more precisely a wave function is localized in one variable, the more spread out it must be in the conjugate variable. Position and momentum are the classic pair. If you force a particle's wave function into a narrow spike in space, high certainty in position, the Fourier relationship implies it becomes a broad spread in momentum space, low certainty in momentum. The product of the uncertainties has a lower bound related to Planck's constant. You cannot make both uncertainties arbitrarily small at once. Heisenberg's principle can be written as a quantitative inequality. The statement is severe to simultaneous precision, and it is not a limit we can engineer away. It is a limit that defines the quantum world. Why does this matter? Because it ends the dream of a classical-like hidden clockwork, where particles have definite positions and momenta at all times, and our only problem is that we haven't measured them. Quantum mechanics is not merely a theory with missing data. It is a theory with different kinds of data. The state of a system is not a list of definite values. It is a wave function or state vector that encodes probabilities for outcomes in different measurement contexts. The uncertainty principle is one of the rules that says you cannot interpret that state as a simple classical set of properties. Nature itself does not allow the classical picture to be fully true. Heisenberg did not present this as a metaphysical sermon. He presented it as a fact of the theory and of the world. Yet it had philosophical impact immediately, because it forced a new understanding of causality and prediction. In classical mechanics, if you know the initial conditions precisely, you can predict the future precisely, at least in principle. In quantum mechanics, even with perfect knowledge of a state, you can only predict probabilities. The future is constrained, not fixed. The universe is lawful, but not deterministic in the classical sense. This is where Heisenberg's work intersects with Bohr's. Bohr emphasized the role of measurement context and classical description. Heisenberg provided a principle that shows why classical description fails when you try to apply it beyond its proper domain. Together they shaped what became the Copenhagen viewpoint, that quantum mechanics is complete as a predictive framework, and that attempts to restore a fully classical picture are misguided. But Heisenberg was not only a theorist of uncertainty, he was also a builder of the new quantum world at a technical level. He contributed to the development of quantum field theory, the understanding of ferromagnetism, and later the mathematics of particle physics. He became one of the leading figures in physics in Germany, a public intellectual as well as a scientist. And then the century darkened. The story of German scientists in the Nazi era is one of the most morally complicated chapters in modern history, and Heisenberg sits near its center. When the Nazis rose to power, many Jewish scientists were expelled or fled. Einstein, Born, and many others. German physics was damaged. Ideological attacks were launched against Jewish physics, and modern theoretical physics was sometimes portrayed as suspect. Heisenberg, who remained in Germany, found himself in a dangerous position. He supported modern physics and did not embrace Nazi ideology, yet he tried to navigate an environment where survival and compromise were real pressures. He was attacked by ideological factions, even labeled a white Jew in propaganda. and he had to defend himself and modern physics within a hostile system. At the same time, he took a leading role in Germany's wartime nuclear research effort, the Uranverein, the German uranium project. This has fueled decades of debate. Was Heisenberg trying to build a bomb for Hitler? Or did he deliberately avoid it? Or was the program simply technically and organizationally incapable? The honest answer is uncomfortable. Motives, capabilities, and choices were entangled. Heisenberg worked on nuclear fission and reactor theory. The German effort did not produce an atomic bomb during the war. After the war, Heisenberg and other German scientists were interned at Farm Hall in Britain, where their conversations were secretly recorded. When they heard about the Hiroshima bomb, they reacted with surprise and confusion, and their discussions revealed that they had not achieved a working bomb design. Whether this was due to moral restraint, technical failure, lack of resources, or a mixture, remains contested. Heisenberg's own post-war accounts portray him as someone who did not want Hitler to have the bomb, but self-portrayals after catastrophe are never clean evidence. What can be said without theater is this: Heisenberg's scientific brilliance exists alongside a historical record that is morally ambiguous and emotionally tense. He stayed, he worked, he navigated, he survived. Many did not. Some people see in that survival a form of compromise. Others see in it an attempt to preserve German science and prevent worse outcomes. The ethical landscape is not easily flattened into heroes and villains. And part of taking Heisenberg seriously is refusing to simplify him to a symbol. Yet even with that complexity, Heisenberg's scientific legacy remains foundational. The uncertainty principle is not a decorative concept. It is one of the central constraints that shapes the behavior of atoms, chemistry, and technology. It explains why electrons do not collapse into the nucleus. Confining an electron too tightly would require an enormous spread in momentum, increasing kinetic energy, creating a stable balance. It underlies the structure of electron orbitals and the periodic table. It shapes tunneling, the phenomenon that allows particles to pass through barriers they cannot classically cross, a phenomenon essential to nuclear fusion in the sun and to devices like the scanning tunneling microscope. It is woven into the behavior of semiconductors, into the stability of matter, into the fundamental limits of measurement. Perhaps the most profound aspect of uncertainty is what it says about knowledge. It says that there are questions that cannot have simultaneous precise answers, not because we are weak, but because the world is structured that way. It forces a humility into physics that classical certainty did not require. It also forces a new kind of creativity. Rather than chasing impossible precision, we learn to work with probability, to design experiments that reveal complementary aspects, to build technologies that exploit quantum constraints rather than fighting them. Heisenberg's own intellectual style reflects this. He was willing to abandon classical visualizations when they blocked progress. He was willing to trust mathematics as a guide to reality, even when it produced unfamiliar structure. Yet he also cared about meaning. His later writings reflect an ongoing attempt to interpret quantum theory in a way that respects both its success and its strangeness. If you want an image to carry away, picture the North Sea island not as romance, but as concentration. A young physicist, not yet 30, deciding to let go of the orbit, letting go of the comforting picture, and building a mechanics out of what can be measured. Then picture him realizing that the algebra he has built contains a new kind of limit, that the very order of operations matters, and that this implies a bound on knowledge itself. That bound is not a defect, it is a feature. It is a signature. It is the mark of the quantum world. You have been listening to Scientific Giants Who Changed the World. Today, we followed Werner Heisenberg from the collapse of old quantum models into the creation of matrix mechanics and the articulation of the uncertainty principle, a constraint that sits at the heart of nature's smallest scales. In our next episode, we will meet Erwin Schrödinger, whose wave equation made quantum mechanics calculable in a new way, and whose thought experiments, especially a cat in a box, forced the world to confront the weirdness we would rather ignore. Until then, thank you for your attention and your time. This episode is written as a continuous story for the ear, because the uncertainty principle is not a trivia fact. It is a turning point in what physics believes about reality, and a turning point in what humans must accept about the limits and power of knowledge.